Hi everyone. In this video we are going to cover section 4.6, limits at infinity and asymptotes. And in this section we add in a few building blocks that ultimately lead to the end goal by the end of the section of following a set of steps to sketch a reasonably accurate graph of a function using various techniques of calculus. Okay, so the first topic that we encounter are limits at infinity, and we can see with these, we have this function here, f of x equals 2 plus 1 over x. Okay, and what we want to talk about initially is what happens when x gets really, really big, right? When x is 3, 4, 5, 6, 7, 8, 9, as it continues on to the right, the function, the blue line, gets closer and closer to the horizontal line y equals 2. And as x gets really, really, really negative, it goes in the negative direction, it also approaches the horizontal line y equals 2. Okay, that horizontal line is called a horizontal asymptote. And when we talk about x getting really, really big, that is a limit at infinity. So I will define both of those, and then we'll go through one example involving a limit at infinity. So if you want to pause the video and read through them, you can. But we have a limit at infinity defined up here. The values of f of x become arbitrarily close to some number L as x gets sufficiently large. As x gets bigger and bigger, f of x gets closer and closer to L. That's what we saw on the graph above. And then that's how we define a limit at infinity. And we can also approach negative infinity. And then that L, that number that we're approaching, getting closer and closer to, that's called a horizontal asymptote. So this function here, if we want to take the limit as x approaches infinity of 5 minus 2 over x squared, what we can do first is use our limit laws. Limit as x approaches infinity of 5 minus the limit as x approaches infinity of 2 over x squared, and break that limit up into two pieces that are easier to work with. The first piece, we have the limit as x approaches infinity of 5. The limit, that line is horizontal, so the y coordinate, the f of x, is always 5. So that part of this limit is just 5. And then the question is, what happens as x gets really, really big to that fraction 2 over x squared? So I want you to think for a second, if you put a really, really big number in that denominator and then square it, and then do the division, what's going to happen? What's going to happen if you use an even larger number and an even larger number? Well, that fraction is going to go to 0. That limit approaches 0. So overall, this becomes 5 minus 0, which is just 5. So that limit is equal to 5, and if we were to look at a graph of this function, we would see a horizontal asymptote also at 5. The same thing will happen if we were to investigate the limit as x approaches negative infinity of that quantity 5 minus 2 over x squared, because even if you plug in a really, really big negative number into that denominator and then square it, oh, it's positive again, but it doesn't even matter. 2 divided by a really, really big negative number is also 0. So even if we approach negative infinity, the limit is still equal to 5. Now, some functions might not approach a finite number as x gets big. So some functions, when we take limits at infinity, the limit will be infinite itself. So we write the limit as x approaches infinity of our function can also be equal to infinity, or it can be equal to negative infinity. And that happens when f of x becomes arbitrarily large for x sufficiently large. And that seems like strange wording, but an example, a graph example, would be good old parabola. My f of x is equal to x to the second power. There's my x-axis, there's my y-axis. So if we look at that function and we take the limit as x approaches infinity of x squared, well, that just keeps getting bigger. As x gets bigger, f of x gets bigger like forever. So that limit is infinity. That limit at infinity is infinite. If we look at a cubic function, that graph, oops, there we go, x, y, that graph looks like this. It's that. There we go. This is f of x is equal to x cubed. So if we take the limit as x approaches, in this one, if I take the limit as x approaches positive infinity, I'm going to get the same answer, positive infinity. But if we look at the limit as x goes to negative infinity of x cubed, that you can see in the graph, it goes down forever. It is equal to negative infinity. And that's because when you cube a negative number, the answer is still negative. Okay, so when I square a negative number, the answer flips to positive. So that's why the parabola up above, they both go up to positive infinity. But when I'm cubing, right, that the negative numbers still keep going down. They still keep getting more and more negative. When we talk about end behavior of functions, it's similar, and you can see in the example here, we're just looking at limits as we approach positive and negative infinity. So for each of these, A and B, right, we talk about the end behavior. That means, you know, what happens as x gets big in the positive direction and in the negative direction. So for A, similar to the last slide, if I have the limit as x approaches positive infinity of negative 5x cubed, well, another one of my limit laws that says that I can factor that negative 5 out and just focus on the x part. Negative 5 times the limit as x approaches infinity of x to the third power. So that's infinity, a really big number, cubed is even larger, but then multiplied by that negative 5 would make the answer negative. So this one is negative infinity. Again, big number cubed times negative 5, the answer is negative infinity. If we're approaching negative infinity of negative 5x cubed, you know, what happens there? Well, now we have a large negative number cubed and then times negative 5. So this is negative 5 times really big, and you could check it in your calculator. Use a big negative number, really big negative number, and that answer is negative infinity. Okay. For the 2x to the fourth, I'm not going to write this one all out. F of x equals 2x to the fourth, but both our limit as you approach positive and negative infinity on that one, those are both positive infinity for both of those limits. Okay, big number to the fourth power, whether it's positive or negative, big number is positive in the end. The process becomes a little bit more involved when dealing with rational functions, functions that are fractions. And the most straightforward step to show what the end, or to determine what the end behavior is for rational functions is to divide by the largest degree in the numerator. Okay, divide by the largest degree in the numerator, and then you'll see what happens. And I'll explain in the example here. So for part A, if my function is 3x minus 1 over 2x plus 5, and I want to take the limit as x approaches positive infinity, 3x minus 1, 2x plus 5, the key step in seeing what is going on here is to divide numerator and denominator by x, the largest degree in the numerator. Okay, and what happens there, that distributes to all four of those terms. So what do we get? Let's see. Limit x approaches positive infinity. The 3x, the x's cancel. 1 times 1 over x is 1 over x. 2x times 1 over x, the x's cancel. 5 times 1 over x is 5 over x. Like that. And then when you approach infinity, this term becomes obsolete. 1 divided by a big number. That term becomes 0. And all you're left with is 3 over 2. Kind of cool how that works out. And that process can be applied to both B and C. Okay. Oh, and by the way, if we were approaching positive or negative infinity on this one, it doesn't matter, right? The fractions still go to 0, and your answer is 3/2. Now, if I do the same thing in part B, I want the limit as x approaches infinity of 3x squared plus 2x. divided by 4x cubed minus 5x plus 7. I'm going to take and multiply, well, actually, I'm dividing by, but I'm showing it as multiplication, the largest degree in just the numerator, but I'm applying that to both the numerator and the denominator. Okay, and I'm left with the limit. X goes to infinity. Let's see. The first term becomes 3. The x squareds cancel out. Second term, 2 over x. One of the x's cancel out. In the denominator, x squared cancels out. We're left with 4x. 5x over x squared. 5 over x. And then 7 over x squared. And hey, look at what happens again. Lots of stuff goes to 0. That term, gone. That term, gone. That term, gone. And, well, we have this 4x left. What happens there? Well, as x gets big, there's an x term in the denominator of that fraction, so the remaining 3 over 4x, that fraction approaches 0. Hey, this limit is 0. And up at the top of with the problem, the note, it says the degree of the numerator and the denominator are the same in the first one, and we got that fraction. The degree of the numerator is less than the degree of the denominator, and hey, we got 0. So that relationship, that play between the degrees in the numerator and the denominator really, really impact what's going on with these. Okay, so I'm not going to do the third one the same way, right? For part C, let me scroll down a little bit, move the next example down. For part C, let me write it down first. My function is 3x squared, the limit. The limit as x approaches infinity of 3x squared plus 4x divided by x plus 2. As x gets really, really big, this x squared in the denominator, that matters a lot, right? These terms are less important because they're not going to grow as fast as that largest term. In part B, the 4x cubed right here, that was the largest degree. That took over, pulling that, or making that denominator big and pulling the size of that fraction down to 0. Here, this term is going to get really, really big. That becomes the most important, and what ends up happening is that limit is equal to infinity. All right? That's kind of cool. And if that explanation didn't make sense, you can still use the same approach. Multiply by 1 over x squared and distribute it to each term in that fraction. We have one more example at the bottom here involving a radical, and if I want to know the end behavior for my square root function, I'm taking, in this case, the limit as x approaches infinity of 3x minus 2 over the square root of 4x squared plus 5. Okay, I would encourage you to try some of these with large values of x, use parentheses, type them into your calculator, and see what happens. Okay, but if I want to establish, what is the degree of x in the numerator and the denominator, well, I can clearly see that the power in the numerator is x to the first power, and then the power in the denominator, now the x is trapped under the square root, that's okay. The power in the denominator is x to the first power also. Do you see that? Right? The square root of x squared is x. So the degree in both the numerator and the denominator is equal to 1. They're the same. The degree is equal to 1. So in the end, what ends up happening, if I'm taking the limit as x approaches positive infinity in this one, what we end up with is the ratio 3 over 2. The 3 is the coefficient of x, and the 2 came from the square root of 4 right there. And I could, again, do this the same way, multiplying by 1 over x in the numerator and the denominator. It would look a little bit different in this one because of the square root, but what ends up happening is I get this 3/2 here, okay? And that's kind of cool. So even though I can't take the square root of 4x squared because it's stuck under the radical with the 5, but as I approach infinity, that 5 doesn't really matter, right? As I approach infinity, the size of this part really, really matters, right? A trillion is not that big of a difference, is not that far off from 1,000,000,005. That's kind of what's going on, what's underlying that concept. And we finally get to the point where this section has been building, where this chapter really has been building, is using calculus and derivatives and limits to sketch pretty accurate graphs of functions. So you should pause the video or look it up in OpenStax and read through each of these 6 steps. I'm going to go through just one example where I follow each of the steps on the next slide, but OpenStax has a whole bunch more for you to take a look at. So you definitely should look at more than just my one example and before you try some of the homework problems. Okay, here's the example. We're going to sketch a graph of f of x equals x minus 1 over squared times x plus 2. And I'm going to follow the 6 steps from the previous slide. Step 1 is the domain. Okay, if that function were all expanded out, it would be a polynomial. So my domain is all real numbers. Okay, there are no holes, there are no asymptotes. The domain, it's a polynomial, so the domain is all real numbers. Step 2, x and y intercepts. X, y intercepts. Okay, for my y-intercept, or actually I'll do x-intercept first. We're going to set the equation equal to 0 and solve. Now, they were nice enough to give us this one factored. Set it equal to 0 and solve. So since it's already factored, I can see that my 2 solutions are positive 1 and negative 2. Positive 1 and negative 2. Then for my y-intercept, and actually let me circle them in red because I'm going to need those later when I go to graph. My y-intercept, we evaluate the function at 0. When x is 0, we have 0 minus 1 squared, and then times 0 plus 2. Negative 1 squared is 1 times 2 is 2. So that actually gives you 3 points pretty quickly. We have on the x-axis 1 comma 0 and negative 2 0, and on the y-axis 0 2. So far so good. Moving on to step 3. Step 3 is the end behavior. The end behavior. So I want to know what is the limit as x approaches infinity and the limit as x approaches negative infinity of my function. Now, for this one, it makes sense to have the function out in its expanded form. So if you distribute all those parentheses together, what you should end up with is x cubed minus 3x plus 2. Same deal for the other one, x cubed minus 3x plus 2. All right, and in looking at the limit, the most important piece is the largest degree, the first term in this case, but the largest degree of x. That tells me what my end behavior is going to look like. And since it's cubed, when you cube a very large number, the answer is very, very large. When you cube a very large negative number, the answer is still negative. So as x approaches positive infinity, the function blows up to positive infinity. As x approaches negative infinity, the function goes down to negative infinity. Step 4 is asymptotes, and we have none because we are defined for all real numbers. No asymptotes. When you get to one with like a fraction, that one might have a vertical or horizontal asymptote. Step 5, calculus. Oh, finally. Well, we did limits in step 3, but this is where we do the real calculus stuff. Step 5 is the derivative and intervals of increase and decrease. So my first derivative, f prime of x, 3x squared minus 3. Okay, then I can get my my critical points by factoring x squared minus 1 equals 0. And then we're going to get 2 critical points. X is equal to plus or minus 1, because that factors into x plus 1 times x minus 1, and you set that equal to 0. All right, so now with step 5, I'm going to draw my number line and see what happens inside of each of these intervals. So I'm going to take the derivative at negative 2, the derivative at 0, and the derivative at positive 2 and see what the sign is. If I plug positive 2 in, 2 squared is 4 times 3 minus 3, you get a positive answer. We are increasing. You plug 0 in, 0 minus 3 is negative. We are decreasing. You substitute negative 2 in, square it, positive 4 times 3 minus 3, positive. Greater than 0, we are increasing. So that tells me that at positive 1, comma, some y coordinate, we have a local, let's see, well, what happens at positive 1? We go from decreasing to increasing, so that would be a local minimum. And at negative 1, comma, some number, we go from increasing to decreasing. That is a local maximum, local max. And how do you get those y coordinates? Well, plug into the original function. Pause the video, type substitute 1 into the original, and then negative 1 into the original, and you should get, let's see, where did I write my answers here? 1, comma, 0, and negative 1, comma, 4. All right, last step, and then we can graph. Step 6 deals with our intervals of concavity. So we need our second derivative. F double prime of x is equal to 6x to the first power. And if I set that equal to 0, there's not a lot of work to do there. Divide by 6. I'm going to draw my number line, a little wavy there. That's okay. 0. The second derivative evaluated at 1. And the second derivative evaluated at negative 1, a number on either side of 0. 6 times 1 is positive, so we are concave upward. 6 times negative 1 is negative, so we are concave downward. All right, and 0, what was my y-coordinate for 0? I got it earlier. Oh, that's right. 0, 2 is an inflection point. Inflection point. There we go. Okay. Whoa, lots of work. Let me zoom back on that a little bit. So we just did all that work. And now, here's the fun part. Put it all together and make a beautiful, perfect graph. No, not beautiful and perfect. We're going to sketch the graph, a reasonably accurate graph of this function. So I'm going to draw myself some axes. If you have graph paper at home, feel free to use it. I just have my tablet, which I probably could find a picture of graph paper, but I want to just show you how we can sketch it by hand. I'm going to scan over my work, figure out what I want on my axes for scales. I just need to go out like a few units in both directions. So I'm going to go out to like 5. I don't even need that much detail, but that's how far out I'm going. 1, 2, 3, 4, 5. Left 5. Up and down 5. Down 1, 2, 3, 4, 5. Okay, I'm going to plot points. 1, 0 was the first point we found. Negative 2, 0. And 0, 2. Those were all found in step 2, right about there. The end behavior, I know we're going up to positive infinity, down to negative infinity. Okay, those aren't part of my graph. That's just kind of a reminder. No asymptotes. My local max and min, let's see, I already have 1 on there. I also need negative 1, 4 on my graph, right about there. And you can kind of see how this is starting to take shape. Okay, so the graph does this. Kind of connect the dots now. Try and draw a smooth curve through. Like this. And then up like that. And I'm a little bit too pointy, a little bit pointier than I would like, but that's okay. I'm going to erase those arrows now. Okay, so let me zoom in on this. So you notice here we're increasing to negative 1. Oops, there it is. We're increasing as we go up to negative 1, decreasing till you get to positive 1, and then increasing onto infinity. Okay. My graph, the concavity, like I said, I'm a little bit pointier than I would have liked, but the concavity, I'm concave downward over everything that I just kind of highlighted in that blue. And then after the inflection point, the graph switches to be concave upward. Cool how that works out. All right, and there we have a reasonably accurate representation of our graph with the using those 6 previous steps there. Okay, so this video was a little bit longer, but now we have reached the end. Please try some of the homework problems. Let me know if you run into any issues or want to see any more examples. Let me know. Thank you very much for listening. Have a wonderful day.